So on your formula sheet, you should have a section that covers the formulas for common collector. And what we use a common collector for. What do we use common collectors for? This is yours. I don't need the answer sheet. Y'all keep answering. So what do we use common collectors for? So it has a high input impedance and a low output impedance, so that's what we do. So we use a common collector to drive low impedance loads or low resistance loads. So this is the output on the power supply. Because when we start loading a power supply, we're dealing with low resistance loads, right? You understand? So we use common collectors to drive power supplies. We use common collectors to drive speakers. We use common collectors to drive motors. That requires a lot of current, right? You understand that? Because motors have fairly low output resistance. So, but it comes up, so high input impedance compared to common emitter. So this is the formula. It's basically the same thing that we use for common emitter that's not bypassed. So it's always R1 in parallel with R2 in parallel with beta times RE. We'll never use RE prime for common collectors. It's got a very low output impedance. If we got a load connected, it's going to be RE equal to RL, or Z out, I'm sorry. The output impedance, by the way, of the amplifier is actually RE. But Z out, which is what we use to calculate gain, Z out would be equal to RE over RL. Now, if RE and RL are the same, then it's just RE, right? You understand that? So a lot of times the load is RE. Input and output are what? In phase. Voltage gain is we use 1, even though it's going to be slightly less than 1 because of this guy right here. Because that AC voltage coming into the base has to go through RE prime. And if you go through a resistor, and even if it's base current, if you push a current through a resistor, you're going to get a what? V is equal to I times R. So that means the input and the output voltage cannot be exactly the same, but the only difference between the input and the output is how much voltage is dropped by RE prime. So for all practical purposes, we're going to say this thing is equal to approximately 1. But it's got a good current gain on it. So the current gain is always greater than 1. Now this is pretty neat in that we can use, since V is constant, so if we use V out and V in is the same, then we can calculate current gain a lot easier. So this is the way we came up with the formula. We know AI is equal to I out over I in, right? Okay. So if V out and V in is equal, then this would also equal to what? V out divided by Z out, or R out, divided by V in divided by Z in. Y'all understand that? So what we're doing is we're calculating the currents. And then what we do, we would invert and multiply. So I could write on this. So we're doing V out divided by Z out. Right? You understand? This would give us what? This would give us I out. And then we're going to divide that by V in divided by Z in. Y'all understand? How do you multiply fractions? You invert the second one and multiply, right? So that's going to be V out. How you divide fractions? Did I say that right? Over Z out times Z in over V in. Of course, we're going to put that together. These two are going to cancel each other out. Why? because they're about the same, right? So that means we can calculate current gain on this guy by using what? Z in over Z out. Y'all understand that? Real easy, but it's real neat on this guy. How much voltage gain do we get? 1, right? Current gain is real easy to calculate. Since we don't get any voltage gain, that means power gain and current gain are the same. So AP and AI are equal to each other. Because I'm taking a higher current but multiplying it by the same voltage, right? You understand that? So once you calculate on this guy, once you calculate your current gain, you calculated your power gain. They're exactly the same. Of course, these are just equations we're not going to use. What we're going to use here is what? 1. We're not going to deal with impedance matching. The formula gets a little hairier when you come up here and try to calculate your impedance matching. But we're not going to worry about that in this class. I just showed you all the formulas. So there's actually some more complicated formulas, but this guy here is not hard. This guy, in my opinion, this guy is easier to calculate than the emitter. And why? We don't have an RC, right? It's never bypassed. So what's VC? Huh? VC is VC. Yeah, VC is VCC. So they're equal to each other, right? You understand that? Very easy. The input and output are out of phase. So this is the input impedance. This is the input that my AC sees. Comes through this, goes up, goes through VCC because it considers this to be a common, right? You understand that? Comes, goes down, comes it, goes through the transistor, goes through RE, goes to the capacitor. We're going to ignore the capacitor because it's going, if we choose it the right size, the reactance of the capacitor is not going to be enough to affect the circuit anyway, right? And goes through RE. So the input impedance is a little harder to see, but we're not dealing with that in this class. But if I was going to calculate current gain, that's what I would have to do. If I was going to try to measure it, I would measure it right here. Oh, I need to show y'all something about the lab here before. And this is the output circuit right here. So the output resistance would be equal to what? RE in parallel with the load, if you do have a load. A lot of times you'll see RE and the load are one and the same. So if I was going to run a motor, we got two options if I'm going to run a motor. We can come up here and we can run a motor here, a DC motor. Okay. Right? Or we could come up here and I could run the motor down here. And of course, this would be running it as a common emitter. This would be running it as a common collector, right? What would be the advantage of these? Well, if I was going to run it, let's say from a digital supply, and my input was 5 volts, and I wanted to run a 12 volt motor, and that would be 12 volts, then I would use this guy right here, because I can get a voltage gain out of a common emitter, right? So if the motor the voltage I was going to run the motor on was lower or higher than the voltage I'm trying to control it, then we'd use a common emitter. If the voltage was going to be the same, so if I was in a digital circuit and I was running a 5 volt motor and the motor is going to generate 5 volts, then odds are we would run it down here. Makes sense? So if your voltage don't change, we'd run it in the emitter. If it does change, we'll run it on the collector. And by the way, we would probably come up and do this. Why would we do that? We call those counter EMF diodes. Why? Protect your transistor so your motor can't generate back into your transistor. We have, for one thing, it's got a bunch of coils in there, right? Y'all understand that? And if we take the power off the coil real quick, then that motor would induce a voltage back into my transistor and pop it, right? Also, when you turn this thing off, if that motor's got centrifugal, of course, once something's in motion, it wants to do what? Stay in motion. If you take the power off a DC motor, it turns into a generator. So DC motors are pretty neat, especially shunt motors. We can either use them as motors or we can use them as generators. So we need to put that diode there to protect our transistor. We would put it up here, but we're going to reverse bias it. So that way when the motor tries to generate, it'll turn it into a... Are you okay there? Let's see. Output impedance used for impedance matching. So the output impedance is pretty complicated. So the formulas are basically the same, guys. So let's calculate this. Can y'all calculate this? What's the first thing I'm gonna calculate? VB, right? What would VB be? We could probably do this in our head. Voltage divider formula. VB would be equal to 10K over 20K. We can mark the K out. Why can't we mark the K out? It's on top and bottom times 10 volts. So this is going to be setting at 5 volts. So normally, you know that's 1/2, right? Everybody okay? Of course, we knew that without even putting the formula up there because we got 12 volts. We got 2 resistors that are the same size, right? You understand that? Okay. So what would be right here? 4.3 volts, right? That's not a phone call, by the way. That's an alarm telling me. Okay, so what would we have now? So I could calculate IE. IE would be equal to 4.3 divided by 1K, which would be 4.3 milliamps. What else do we need? Well, I guess we do need to do that. Voltage gain, what's voltage gain? What's voltage gain? 1, good. It's not exactly 1, but it's close enough. It's kind of like emitter current and collector current, right? You understand? So what we got to do to calculate the power gain on this thing, we need to calculate our this one parallel. So here goes my AC. Comes flying in, goes through the capacitor. If we choose the capacitor the right size, it's not. We're going to ignore it, right? Comes over. Here's that point. What does it do? Goes up. Goes through the power supply. AC sees the power supply as a short circuit. We actually looked at that, right? It's going to go down. Going to go this way. It's going to fly through here. Now we're doing signal flow. I know current flows. It's just easier to see the way the signal flows and try to, instead of trying to figure current. Goes here. Goes here. Okay, guys. So what would be the formula for Zn or Rn? It's going to be R1 in parallel with R2 in parallel with beta times RE in parallel with RL. So what we probably need to do is solve for this guy here first. And y'all can do this. You got to show your math, but so that's 1K in parallel with 1K. What's 1K in parallel with 1K? Don't pick up a calculator. They're the same size. Anytime you got something that's the same size in parallel, it's 1/2, right? You understand? So that'd be 500 ohms. So that'd be 500 ohms times beta. What's the beta? 175. So this is Z out. So what's Z out equal to? 175 times 500. Y'all understand that? Anybody got any questions on that? What's that? 87.5K. Are we okay? So Zn would be equal to, or Zn or Rn. Y'all mind me calling it Zn? Are y'all okay with that? Would be 1 over 10K plus 1 over 10K plus 1 over 87.5K. So we know it's going to be less than 10. It's going to probably be less than 5K. Because I know these two in parallel right here is going to give me 5K. This right here is not going to affect it, so it's going to be real close to 5K. What y'all got? What we got? Four K, four, or high threes or low fours. $4.7K. So my current gain, which is going to be my power gain, would be equal to Zn 4.7K divided by Z out, which is 500 ohms. So what's our current gain? What's our current gain, guy? 9.4. So what's our power gain? Y'all understand that? Because we don't get any voltage gain, and power is equal to V times I, right? So if I took So any questions on what we've done so far? How many dB would that be? So 9.4 log times 10 will be 9.7 dB. Came up real close because their number's almost 10. And that's the common collector. So what's different? It's a little different on how we calculate Zn, right? That's a little different. So when we calculate Zn, we have to visualize the AC circuit coming in. And when the AC comes this way, it always splits this way. RE is never bypassed. On a common collector, RE is never bypassed. So we got a pretty high input resistance of 4.7K. We got a pretty low input-output resistance of about 500 ohms. So anything y'all need to see on that? Y'all think y'all can work a few of these on a worksheet? Yes or no? Huh? Well, it's gonna be. Y'all know y'all got a worksheet on this, right? And you know there's gonna be one of these on the next test, right? Probably 2 on the next test. We'll probably have a common emitter and a common collector. There's gonna be some power supply questions on the next test. There's gonna be Zener. That dang reverse bias diode is gonna be on the next test. Yeah, we'll see. 5 volts, 4.3 volts. Let me erase this. So here comes the answer. Zn is 4.8K, Z out is 500 ohms, AD would be equal to 9.6, which is equal to AI, which is 9.8 dB. Pretty easy. These guys here are pretty easy to calculate. So what do we use these guys? Well, we use these guys to match a high impedance to a low impedance, right? These guys here they'll give you tons of current gain, but they don't give you any voltage gain. But that's no big deal. We can use common emitters. So this is why amplifiers go in what? They go in stages, right? The first amplifier, we want it to have high input impedance because then as we go through, we're going to start lowering the input impedance, right? You understand that? And eventually, we're going to usually drive a low impedance load, and that's where we're going to use this common collector to drive those speakers, to drive those solenoids, to drive those very low impedance circuits or low resistance circuits. Oh, we already talked about this. You okay? We call this what? Now read it up there in the fine print. We call this a Darlington pair. What do we use Darlington pairs for? So if I needed an extremely high input impedance, and we can use Darlington pairs, and of course this would be a common collector. But what we get on a Darlington pair, if this right here had a minimum beta of 30, and then this guy here had a minimum beta of 30, then what would be the total beta of the circuit? I don't think so. What would be the total beta of the circuit? 30 times 3 is 90. This is not 30 times 3. This is 30 times 30. So this guy right here would have a beta of 900. This resistor over here is seen as times beta, right? So if this was a 1K resistor, the base over here would see it as a 900K. So this is the guy that would match an extremely high input impedance to a very low impedance, right? These guys right here, these Darlington pairs. And they're so common that we can buy these things in a single package. They have 3 leads coming out of it, and they're integrated circuits. They're not transistors, they're integrated circuits. And they have 2 transistors connected to Darlington pair. We use them all over the place. Because you get that what? You get extremely high gains, right? And then this guy over here could be a very small resistor. It don't make any difference because it's seen as beta times beta, right? So I think I showed y'all a Darlington pair that had a beta over 1,000, a minimum beta. Now these are minimum betas, right? You understand it? That sucker had a minimum beta of 1,000. Did I show y'all that one? Yeah, a minimum beta of 1,000. You cannot check these with the diode scale on your meter. Because why? Because you have to break over 2 junctions. It's just like you cannot check an LED with your meter. The VF is too high for your digital meter to put out. So if you're going to check these guys, you're going to have to hook them up into a circuit, right? You understand? And bias them on. And LEDs, if you're going to check them, you need to hook them up to a circuit and turn them on. Or measure the voltage off. This is something that we're going to start seeing on tests. I imagine there'll be 3 questions on there. They'll have multiple answers. So these are different amplifiers, a common base, common emitter, common collector, and these are the characteristics of those. If you want me to, I'll print this off and give this. So common base has a very low input impedance, a very high output impedance. We get a 0-degree phase shift. The voltage gain is high. The current gain is slightly less than 1. And it's got a low power gain. We use these guys in high frequency applications, right? These are the 2 guys that we're studying. Common emitter has a wide input impedance, medium. A high input impedance is high, right? We have a phase shift on a common emitter of what? 180 degrees. So it's going to be a duplicate, but it's going to be the mirror image of it. Voltage gain is medium, current gain is medium, but since we get both a current and a voltage gain, it gives us a very high power gain, if it's designed correctly. A common collector has a wide impedance, high output impedance, very low, right? 0-degree phase shift, voltage gain of about what? 1. Current gain is high, power gain is medium. So these are the 2 guys that we're dealing with here. Common emitter, common. But you need to learn the characteristics of the common base also. Are we okay? Common bases, you calculate them the same too. It's just that input impedance. So what you do on a common base, what do we mean by common? Common base, common emitter, common collector. What's common? What are we talking about? Are we talking about the DC or are we talking about the AC? Well, if we was talking about the DC folks, how could I come over here and bring my input in on this, connect the collector directly to VCC, take my output off the emitter and call this a common collector? Because the collector is surely not common to the DC common, right? But it's common to the what? To the AC. So when we talk about common, it's what the signal is common to. Not not your DC power supply, it's what that AC signal is coming flying through there, what is common to. So what we do is we look at what? So if I look at a common base, I know I'm going to do what? I know I'm not going to do what? I know, so on a common base, we input on the base, and we're going to output on what? I'm sorry, I'm starting off wrong. I got the common collector in my head, I'm sorry. So common base, what we do is we input on the emitter. I should put this in there. And we're going to output on the collector. On the common emitter, what do we input on? Where does our input go to? What lead does the input go to? Common, goes into the base. And what do we output off of? Collector. Common collector, what do we input on? Yeah, we input on the base, and we output on the what? Emitter, yeah. And that's what I try to tell you, and I don't have room to write that, is you don't input on what's common, and you don't output on what's common, right? You understand? So what I do is I look at an amplifier and I see what we input on and what we output on, and then the other lead has to be what? Common. And this is why we get a current gain of slightly less than 1, because we're inputting on the emitter. We're outputting on the collector. So what's the difference between the emitter current and the collector current? Are they the same? Huh? They're close because the emitter current supports both the base current and the collector current, right? You understand? So this is why this guy here has a current gain of less than 1, because we input on the emitter and output on the collector. So I think I'll add that. I don't know how I do that. I guess I could put it on, put them on the same line. I guess I'll do that. Put one more chart for what we input and what we output on. And so this is a pretty good chart. Notice here these don't say equal to 1. These say that's a little squiggly line, which means what? Approximate. So we'll do a worksheet on common emitters. Common collectors. I'll add that to this chart, and I'll print it off and give it to you so you have to download it. And I'll also put it on the internet if you need to. So what's Class A? What's a Class AB amplifier? So we know we have 3 classes. So let's go back and review this. What's our 3 classes? So Class A, we get 360 degrees of the input signal that's passed to the output, right? But Class A amplifiers are very inefficient because we have to bias those transistors on. So all that bias current that we look at, all that bias IC and all that kind of stuff, that's not gain, right? Class B is what? Yeah, but these guys move up to about what? 75%, a maximum 75%. And then we have Class B, or Class C. These guys amplify less than 180, but these guys here are pretty close to 100%. Not quite. So this is Class A. Everybody okay? Here they're showing it out of phase. So this actually would be a common emitter. So here they're showing the input signal and the output signal. So the output is a mirror image of the input, but it's what? It's bigger, right? Of course, that's voltage. This would be a Class B, where we put in an input signal and we only get what out? 180 degrees, right? This is a Class B amplifier. Can you see how this works? So Class B amplifiers are basically our saturated switches. Not too much to it. But if we put AC, what we do is we flip off one of our alternations so it won't break over the diode, transistor. This is a common collector Class B. This is a common base Class B. This is a voltage divider bias. What I want you to do on this one is calculate the base voltage there for me. Can y'all see this? So this is voltage divider bias. This guy right here should be classified B. And notice I'm not using standard resistors to make this work. So what would the base voltage be? So my top resistor is 100K. My bottom resistor is 6,195 ohms. So what would VB be equal to? What we got? 0.7. So is the transistor on or is the transistor off? Huh? Well, let's think about this. Let's go over here. What voltage will we have over here on RE? So is the transistor on or the transistor off? Transistor what? Off. There's no voltage left over for emitter current, right? You understand that? Are we okay? So right now my output would be sitting over here, would be sitting at plus 12 volts, because this is a common emitter. My output voltage over here would be 0 volts. And why is that? How can I have 12 volts here and 0 volts right there? Somebody explain that to me. That's what we're doing. We're calculating bias. Yeah, the capacitor blocks of DC, right? I understand that. So I put an input signal right here. So here comes my input signal. We'll do a sine wave, right? Well, as soon as this thing goes positive, then that's going to turn. Now we have more than 7/10, so that's going to put a voltage right here, right? You understand? Which is going to turn the transistor on, which is going to cause the output voltage to start changing. As soon as the output voltage starts changing, then the output will come up here and do this until it drops down to 7/10 of a volt again, and what it will do? It'll cut off, right? So what would we get on the output? And what class is that? This is class B, 180 degrees, exactly 180 degrees. You'll see how we get that? Pretty neat, ain't it? So to get a true class B, the signal is not supposed to turn the transistor. The signal is not supposed to provide the 7/10 of a load. So what we do is we bias the 7/10 of a load. That makes sense? Push-pull. Now these are called push-pull amplifiers. They're also called complementary amplifiers, and they're also called AB class. So the class is AB. But these are three names. So the class of amplifiers AB. So people call this push-pull, or they call it a complementary amplifier. And what do we mean by complementary? What's the complement? In electronics or electricity, what do we mean when we say the complement? It doesn't mean to say to somebody they look good today. What does that mean? Huh? No. Complement. Some of y'all said DC. Some of y'all said too, complement math. Complement means the opposite of. So what this means is these two transistors have to be complements of each other. So that means what does the complement mean of two transistors? It means they have the same specs. It's just one of them's a what? PNP, and one of them's an NP. So these guys have got to be complementary pairs, or they call them complementary pairs. So ours, we're using the 2N3904. So the 2N30, this guy here would have to be a 2N3906, which is the complement pair. This is the one I hooked up in class the other day. What's wrong with this guy? What little problem did we get on this? Well, as soon as my input voltage, and these are, what am I inputting on? I'm inputting on the base. I'm outputting on the collector. So what type of amplifiers are these? Common, inputting on the base, outputting on the collector. I'm sorry, inputting on the base, outputting on the emitter. Yeah, here's the emitter. So let's just look at one of them. So here comes my input to the top one. It inputs on the what? Base. We're outputting on the emitter. So what type of amplifier are these? Common collectors. Right, you understand. My input starts coming positive. Well, this guy right here is a PNP. This guy over here is an NPN. Which transistor is going to turn on? Which one has the positive on the base? So this guy's going to turn on, right? You understand? So what's it going to do? It's going to pass the positive alternation. Once this gets up above 0.7 of a volt, so what's going to happen is we're going to start off with this, then we're going to start up, it's going to pass the positive alternation, and then it's going to drop down, and then it's going to cut off. Then this thing's going to swing negative. Once it exceeds that, once this guy here exceeds a negative 0.7 of a volt, this guy's going to cut on, and we're going to get this on the output. So what we get on this right now is what we call crossover distortion. Why? Because the input signals have to exceed that 0.7 of a volt to turn it on. Everybody understand that? Okay, are we okay so far? Okay, guys, y'all take a break. Seems like y'all ready for it. You can run it on but if I run it on DC, if I run it on a plus DC, and then a common, then this guy here, we're going to have to bias this thing right in the center, right? So what we would do is we would bias this right here at so what I want this thing right here to be biased at plus 10 volts. So since I have a voltage there, I have to have a what there? A capacitor. Okay, you understand that? So notice these two resistors are the same size. This right here is at, so if this guy here was if this guy right here was at 10 volts, then what would this be at? It's going to be at 9.3, right? And this guy right here is going to be at 0.7. Let's see what's going to work. 20 volts. So this guy right here is going to drop 0.7. This guy here is going to drop 0.7. So what's that guy right there going to drop? Series circuit, guys. We know the voltage drop across these two guys. We know they're going to be 0.7 or 1.4 volts between the two. So what's that resistor right there going to drop? The resistors are the same size. So they got to drop the same voltage. The diodes are dropping 1.4. I got 20 volt applied. The two resistors have got to drop the rest of the voltage. So what are they going to drop? What's that? Well, we're losing 1.4 volts, right? We use 1.4 there, right? So that might be right. So 20 minus 1.4, what's that going to be? 18.6. So you're right. Good. So this guy right here is going to drop what? 9.3 volts. This guy right here is going to drop what? 9.3 volts. Right? We okay? That makes sense? So what the purpose of the if I didn't put the two diodes, it's going to be real hard to calculate, because what I want this thing to do is I want this thing here to be setting exactly 0.7 of a difference between here and here, right? So, I'm sorry, I got this backwards. This guy right here is going to be what? I'm sorry. 9.3. I was looking at this as being the emitter. So this is going to be at 9.3. This is going to be at 9.3. This is going to be setting at 10. There's actually no output. So this guy right here, as soon as the input comes on, right, you understand that, then the output will start swinging. But we got to have that capacitor. Why don't we have to have that capacitor? Because why? Because of the bias. Now come over and do this. what's this guy going to be setting at right here? We're going to bias this thing right here to set it what? 0 volts. Right? These two guys are going to be the same size. So what would be right here? If this is at 0 volts, what would be right here? Yeah, so this will be 0.7. Here's VEE. What would this be at? This is going to be at a minus 0.7. Right? Y'all understand that? So if this right here was, if VCC was equal to 10 volts, and this guy right here was equal to 10 volts, this is minus, right? You'll follow this so far. And this was 100 ohms right here, and this was 100 ohms right there. How much voltage would this guy here drop? So I've got, what's my difference in potential? Plus 10 to minus 10. What's my difference in potential? Plus 10 to minus 10. What's my difference in potential? Huh? What's my difference in potential between plus 10 and minus 10? Huh? 20 volts. So this is the same circuit we did a while ago, right? Minus 10 on this side. So we got a minus 20 on this side. And we got a what? Got a plus 20 on that side. So there's a difference. I'm sorry. Got a plus 10 on this side and a minus 10 on this side. There's 20 volts, difference in potential. We're not doing subtraction here. So this would be like I came over here and I did this. Right? And then this guy right here is 10 volts. And this guy right here is 10 volts. Now, relative to this point right here, if this was my circuit, then this is going to, and this right over here was common, and this over here was common, then of course from here to here I should have what? 10 volts. From here to here I should have 10 volts, but if I go across the two, what am I going to have? 20 volts, right? Y'all understand that? Okay, so that's just like the first circuit. This guy right here is going to drop what? This guy's going to drop 9.3 volts of the 20 volts. This guy right here is going to drop a negative 9.3 of the 20 volts. Right? You'll see that. So this guy, we got minus 10 right there. This guy's going to drop a minus 9.3, so that leaves me with a minus 0.7 right there. We have 0 volts right there. We have minus right there. The transistor's not turned on. Right? You understand? This guy, this drops 9.3 of 10 volts. What does that leave me left out? Over 0.7. There's 0 volts, 0.7. We have no emitter current because there's no voltage on the emitter side. So this guy right here is setting, ready to be what? Turned on. This guy right here is set up ready to be what? Turned on. The input signal does not have to supply the 0.7 of a volt anymore. Right? Because it's already there. So that means this input signal goes like this. This guy here is going to turn on. The output's going to go like this. As soon as it drops down to 0, it's going to do what? This guy's going to cut back off. What's going to happen over here? Then the input signal is going to do this. The output signal is going to do that. What type of output do we get here? DC or AC? We start off from what? 0. We go up. We drop back down to 0. We switch negative. We come back to 0. What is that? That's AC. So these are stereo amplifiers right here. You cannot put DC. We do away with the capacitor. We don't have to put the coupling capacitor in there. So the output of your amplifier is AC. And these guys here are pretty easy. But what we're going to see, so if I come over here and look at a power amp, what I'm looking for is I'm looking for 2 diodes in there, hooked up back to back. And why do they put them in there? Well, those diodes are there to put that 0.7 of a volt on there, right? To put the base at exactly 0.7 or real close to it, so the input signal is not turning the transistor. The input, if I don't have an input signal, both those transistors are what? They're off. So let's go back and see if we can see some schematics on a power amp. And we could calculate this whole thing. I mean, it's really neat, but we're not going to do that. I just want y'all to get familiar with it. So handouts, y'all see a one on a power amp? Let's go to schematics. Nope. I know they're in here somewhere, guys. One of them is a Harman Kardon amp that we've got. Harman Kardon is a big name in power amps and amplifiers. If you're into stereo, they're one of the top makers of amplifiers. So here we go. So this is a pretty standard power amp. Well, it's complicated, though, but it's just common emitter, common collector, common bases. They're turned a little different. Here they're using 4. We'd have to, because they're going through a Darlington arrangement. So if I'm going through a Darlington, I got to go 1.4, right? You understand? So here's the 4 diodes that's up here that's biasing these guys here, ready to be what? Turned on. Here's my outputs right here. Here's the actual output. So this is the right channel. This is the left channel. Okay. Can y'all see that? Okay, I need to point over here. So we come in from here. Here's my left end. Here's my right end. If we don't run it, what we call bridge. Y'all know what that means? So when we get power amps, we got two ways. Most of the time, your power amps, you can run them 2 different ways. You can run them as stereo, which means left, right, or you can run them what we call bridge. Y'all know what bridge is? Bridge is when we take your left and put it in parallel with your right, and we get a mono output. So it means I could have a 400 watt amplifier, and I split it 200 left, right, you understand? Or I could use 2 400 watt amplifiers. I could run them bridged, and now I get 400 watts out of each side. If I'm going to run a bass speaker, I'm going to run it bridged. A bass does not do stereo, right? So if you ever listen to stereo, the bass usually comes out on both of them equal, and what changes is your mid ranges and your tweet and your high ranges, right? So normally, if they run what they call a power woofer or a big woofer, they run that amplifier what? They run it bridged. And what they do when we switch it bridge, basically we take our output from here. We take our output from here to here. So if I was going to run it unbridged, and I can't draw on this, guys, then I would take my output here, and then it would come back to a common. And I would take this, and it would come back to a common. If I ran it bridged, though, I would take my speaker, and I would hook it up between the what? The right output and the left output. And then you run it bridged. Does that make sense? And so you get the full power of the amplifier. So if you ever buy a power amp, that's what you're looking at. These guys still use a ton of discrete components because it's hard to get one integrated amplifier to provide 200 or 300 watts. So we're going to hook a lot of these guys in parallel. Where's the other guy? Yeah, so this is a lot easier to see. So this is the left channel hooked in parallel. By the way, what's the function of the resistors? Well, these are little old tiny resistors. I can't see the size of them. But what happens if these things are not perfectly matched, then what would usually happen is that one of your transistors would try to take the load. But what happens if it tries to take the load, its emitter resistor is going to try to conduct more current, but the emitter resistor won't let it, right? You all understand? So these guys right here are in there to make it balance the load. These are all hooked in parallel. The only thing difference is that each one of them's got their own resistor. And this is one channel, by the way. Where's our I don't see it. This is, I don't know whose power amp this is. And I I don't know what the wattage rating on. Can y'all see the wattage rating on there? And I can't see what the voltage is up here either, guys. This is not a real good print. And this is an AC amplifier. This is not one for your car. So I'll look right here. What's this guy right here? What's this? So what is this? So this is our power supply, right? So here we get, good gracious, I can't see what that is, 70 something volts, 75 volts. It's using it as a center tap. So this would be a center tap coming in. So this would be a fuse both sides. So this would have to run off the center tap transformer. This develops the positive power supply. This develops the negative power supply. It looks like 70 volts to me. So that means we couldn't quite get it, but that would be almost 140 volts peak out. My input comes in here. This would be channel 1. We're inputting on the base, outputting on the collector. So what type of guys? This would be common. This would be a what? Inputting on the base, outputting on the collector. This would be a what? Inputting on the base, outputting on the collector. Right, common emitter, right? Then this guy right here comes flying over. This inputs on the base, looks like it outputs on the collector too. I'm sorry, this is the emitter. So this right here is inputting on the base. This is outputting on the emitter. Can y'all see the little arrow right there? Sorry for me to see. See the little dot right there? Can y'all see the little dot right there? Y'all can't see that little dot? Y'all can't see it's darker right there. Y'all can definitely see it right here. See that? So what's that? That's the emitter. This is the emitter here. So here we're inputting on the emitter, on the base, and we're outputting on the emitter. So what is this one? Common collector. Right? And then we take that and feed it directly into the base of another transistor. Okay. And then we get over here to these drivers. So here we're inputting on the base. We're outputting on the emitter. So this is the what? Yeah. And here we're inputting on the base and we're outputting on the emitter. So these are also common collectors. And then this is the shared line. These are NPN. These are NPN transistors. These are PNP transistors. Right. Common collector. This is my output. This is my negative supply. This is my positive supply. So this guy here is going to generate AC, and this will be a power amp. So normally when we get into these power amps, these guys are still going to be a lot of discrete components. You get inside your car radio, you're probably going to have one IC, and it's going to be mounted up against the metal chassis, and it's going to be everything. You get into these big power amps, and you're going to see a lot of discrete components again. I'll show you a power amp. Okay. Inside your radio, it has an inverter in there. And what does inverters do? You know what inverters do? So a lot of people buy them for their cars. What do they do? What do inverters do? Turns DC and AC. Okay. So I don't know if you've ever looked at a power amp, but the leads coming from your battery to your power amp are extremely big because it's trying to deliver all that power at a low voltage. Right? You understand? So when it comes into the power amp, it goes to an inverter that turns DC into what? AC at a lot higher voltage. Usually it's plus or minus, and then it's AC. Then I can generate a negative DC and a positive DC. Right? Usually it's around 80 volts. and then you look at the wires feeding out of your speakers. How big are those things? Feeding the actual speakers. Huh? Not the speakers. Feeding your power out might be 4 gauge, but feeding your speakers are going to be small wires. I mean, we're getting down to, maybe 14 gauge or something like that, or even smaller, because how can we get 250 amps out of a small wire like that? Huh? Why is the current small? Huh? Yeah, the voltage is a lot higher. So your speaker wires are just standard speaker wires. I mean, there's nothing big about the speaker wires feeding on a power amp. It's the battery, because the battery not only has to deliver the power for the speakers, it's also got to power the amplifier, right? You understand? If we got any Class A's in there, we're going to have to buy those things off. These are mostly Class B's, but these guys are still a maximum of 75% efficient. Right? You understand? So that means if I get 75 watts out, I have to put 100 watts in. Right? So your battery's got to not only power the speakers, it's got to also power the what? The amplifier. Right? You understand that? Which is pretty interesting. I'll try to find that thing and look for it. So what we're going to do next is we're not going to get into, I just wanted to show y'all, so what's the function of the two diodes? It's to take away the what? Prevent that what? Yeah, so what happens, what it does, it buys them until they're ready to be turned on, right? So what it does, it puts exactly 7/10 of a volt on that thing, but it still puts 0 volts on the emitter. Does that make sense? But these guys right here, these two resistors will be the same size. These guys here will be the same size. These two diodes right here, since we're only doing one set, then we use two. That first one I showed you was actually doing